This video is going to focus on half-life as a topic, culminating in the introduction of the equations in order to calculate half-life. The only learning target that relates to half-life is to be able to use the half-life equation to calculate stuff, but you also have to understand the concept. So, when it comes to nuclear decay, when you have a radioactive isotope, which means it's unstable, it's going to try to eject some kind of nuclear particle to become stable, to get to that ratio, the optimal ratio of 1 to 1 or 1.5 to 1. Okay? In order to get to stability, sometimes particles have to go through a multi-step decay, meaning it releases a beta particle and then it's still not stable. So it releases another beta particle and it's still not stable. So then it releases an alpha particle and it's still not stable. And that keeps happening until it gets down to a stable product. Each of those steps in the decay process have their own half-life. So you've listed on the screen over here. That's for uranium-238. Okay? And all of the steps it goes through to get from radioactive to stable. So eventually it gets down to lead-206. And that's stable, which means it's not a radioactive isotope. It won't go through any form of nuclear decay. So first it releases an alpha particle, and then a beta, then another beta, then an alpha. So you can kind of see the progression it goes through. And each listed on the right-hand side is the time it takes for half of the substance to decay. So how this works is, imagine you had like 100 grams of that uranium-238. To get half of it to become thorium-234, you need 4.5 times 10 to the 9 years. Right? And then for that stuff to become protactinium, it's going to take 24.5 days. So each step along the process has its own amount of time it takes. And again, it's the time it takes for half of it to decay. So for that 100 grams of uranium-238, it takes 4.5 times 10 to the 9 years to get down to 50 grams. And then it takes 4.5 times 10 to the 9 years to get down from 50 to 25. So each half-life is the amount of time it takes for half of it to decay. And one thing to realize is as this decays, it's not forming anything stable for a really long time. So it takes a long time for this to actually get to a stable product. The other thing that's really funny is these half-lives kind of combine with each other in that, once 50 grams of uranium has changed, well, in fact, once like 2 grams have changed, some of that is changing from thorium to the next one, and then from that to uranium, and from that to thorium. So it's really hard for us to know at any given time exactly how much of any of these intermediate steps actually exist. You can try to calculate it, but it gets to be really complicated when you don't know exactly how long it's going to take for 10 grams to decay necessarily. We can use an equation to estimate that, but all we really know is that it takes 4.5 times 10 to the 9 years for half of it to decay. Okay, so in terms of half-life and actually calculating how long it takes for something to be stable, it's a more complicated calculation than you would think, especially when things go through multi-staged decay. So half-life, which is what I was just talking about on the last screen, is the time it takes for half of the substance to become a different product, okay, to become a different nucleus, to go through some kind of nuclear change, to become a different isotope. Sometimes it's a radioactive isotope, sometimes it's stable isotope, it just depends on the step. And it ranges in terms of time. Sometimes they can happen as fast as milliseconds, sometimes they can take billions of years to have half of it actually become a different product. So there's a whole bunch of different ones listed in the table. Again, these are ranging from 1.25 times 10 to the 9 years, right, down to fractions of a second. This oxygen-13, 8.7 times 10 to the negative 3 seconds. So almost no time at all for half of it to decay. Okay? And that's part of the deal. Since this is happening naturally and spontaneously, these half-lives are simply determined by the atom, okay? How long it takes. It's something we calculate, but it's not something that we can really guess at without calculating or explain. If you were to look at a graph of substances, so this is bismuth-210, and it takes exactly 5 days for it to decay, for half of it to decay. So if I have a 100-gram sample, in 5 days you'll have 50. And then if I have that 100-gram sample, 5 days later, you're down to 25. So one small misconception about half-lives is that if it takes 5 days for half of it to go away, in the next 5 days, the other half will be gone and you'll have none left in 10 days. And that's not how it works. It halves itself, half and half and half and half, until you get down to, really near zero. And then, you think about that, like if you half and half and half and half, you never get to a point where all of it is changed. We find in reality there will be eventually a time when all of it changes, but we can't predict for those last few exactly how many half-lives it will take. Okay, that last particle that's going to can be converted to something else, it's hard for us to predict exactly how long that will take. If you've done any kind of graphing, if you look at this graph over here of half-lives, this is an exponential decay. Okay, this is like a first-order rate law. Exponential decay as you change into a different form. And I have a simulation here I'm going to show you that actually has materials going through half-lives. It's kind of cool because you can see how, first of all, this half and half and half and half kind of looks. And then second of all, we'll actually look at like two-step decompositions to see how they affect one another. Let's take a look at this box up here. We're going to start out with beryllium-11, and it takes 13.81 seconds for beryllium to become boron-11. So if I start this, you're going to see the particles change, and you're going to see a graph start to be made. Okay, so the particles are changing to blue because they're making boron-11. Okay, and very quickly, it takes 13.81 seconds for that first 50 to disappear. So you see a lot of blue being produced right at the beginning here. And then once that first half-life is kind of finished, it starts to go a little bit more slowly. Right? And we can see down here on our graph this is happening, right? The yellow is decreasing, but the amount of blue is also decreasing in terms of the rate at which it's being produced. Your slope is getting a lot more flat. Okay? And that's 2 half-lives, so now it's taking even longer at this point. 3 half-lives, we've still got some yellow hanging on, okay? And it's just halving each time these half-lives are hit. And eventually we will get to a spot where there won't be any yellow left. It's just a question of number of half-lives that it would take. Okay? Your slope on your blue line is almost flat at this point, but it still is going up as you continue to have the particles decompose. Okay? So one thing you notice about these graphs is that right away, always, they dramatically increase or decrease. Okay? That first half-life, where you half the materials disappear, it goes really fast. But then when you half and half and half and half, it goes a lot more slowly to the point where it's hardly changing anymore, but it still is changing. Okay? If you look at your screen right now, we've got 6 left, 5 left, right? 3 left, all of a sudden 2 in at the same time. It's hard to predict, right? 2 left. And those last 2 hanger-ons, if we can see if they go or not. 1 left. And that last one is super hard to predict when it will actually disappear. Okay, we don't know how many half-lives it takes for the last one to disappear always, because sometimes after 1 half-life, it's still not gone. Okay? And there, it's finally gone. So if we reset this, we can look at one that's a 2-step decay. So oxygen's going to decay to fluorine in 13.5 seconds, and then that fluorine's actually decayed to neon in about 11 seconds. And again, one thing to keep an eye on here is that as oxygen decays to fluorine, fluorine will also start decaying to neon. And all 3 of these particles are kind of trying to establish some kind of balance between them as they all go through half-lives. So the yellow becomes blue very quickly, and we see green starting to show up pretty quickly also as it's starting its own half-life of the blue materials. And if you look at your graph, the yellow and blue, right, are increasing and decreasing right away. That green line, it takes a while for it to get going because you need blues to exist to get the greens to decay. But we eventually have where the green takes over because you have enough blues now to help that green's first half-life. Okay, it just depends. So our amount of blue diminishes greatly as our greens replace it and go through multiple half-lives. So you can see it's kind of a battle between all 3 of them as the decay, and it's hard for us to predict at any one moment exactly how much there will be of any one substance. but we can predict kind of independently how much each process should take. So you can see now here, not many yellow left, some green left, or some blue left, but a lot of the blues are turning into green as fast as they can, as fast as that half-life will allow. So if you take a look, hopefully there'll eventually not be any yellows left, right, as all the yellows turn into blues, and then all the blues will actually turn into greens. So that's just a simulation to show you kind of how half-life works. Again, to show you specifically, like now, how long it takes for some of those last particles to actually convert to a different particle through nuclear decay. So there's an equation to relate the half-life to the amount of materials, and it's this equation on the screen. And the truth is, most of these variables you've never seen before. So I gotta run through them. A is the amount of substance left. Left is really important here. A sub naught, or A0, is your original amount. That's your starting amount. Okay. And then it's 1/2 small t, which is the amount of time that's gone by. And then big T, which is the half-life. And the one thing about small t and big T is to make sure you're in the same unit. So if your half-life is measured in seconds and you try to do your elapsed time in minutes, it's not going to work out for you. So here's an example problem. Iodine 131 has a half-life of 8 days. Gosh, how many grams would be remaining of an 80-gram original sample after 3 weeks? So our original amount is this 80 grams. We're looking for how much will be remaining, so we're looking for A. Your half-life, right, given to you is 8 days. And your amount of time elapsed has been 3 weeks. 3 weeks and 8 days are not in the same unit of measurement, so we got to make that 3 weeks into days. 3 times 7 is 21 days, so we'd have 21 days divided by your 8-day as your superscript up here. So there it is, all filled out. If you calculate that, then you'll find you have 13 grams left. So this equation is really great in calculating amount of stuff left over or the amount of stuff you originated with, but it's really hard to calculate a half-life from this equation. Now, this is an example problem where if you were going to calculate half-life, it's tricky. What I have for you is a rearranged equation. And since you're doing this test online, you can actually just use these equations. You just need to know how to use them. This equation is not a different equation than the one on the other screen. It's just a rearrangement using logs, which is something that's challenging for a lot of people. So this equation can be used instead. Same variables. Big T is your half-life, small t is the amount of time that's gone by. A sub naught is the stuff you started with. A is then what you finished with. So if you're going to plug in the numbers from this problem right here, the amount of time that's gone by is 600 seconds, right? ln of 2 was just calculated to be 0.693. A sub naught, your original amount, is 500, and then you eventually have only 16.63. So if you calculate that, you'll get a half-life of about 122.2. We're going to do more examples with these problems tomorrow and actually do a lab on them tomorrow. But the form will ask you to do a little bit of calculating with this too, for me to see if you can manipulate these equations. Okay, have a nice night. I'll see you guys tomorrow.